Hey folks, Sonic fan here, and today I'm taking apart a Fellows Laminator. This video is going to be a little lower quality because I lost my camera, um, so yeah, it's not going to be as good as usual. It says it's 1080p, but I don't think so. Anyway, I might make a new trend of showing the music I'm listening to while I've been doing my repairs on my latest albums, since I do love collecting vinyl records. So a quick shout out to Gloria, Estefan, the Miami Sound Machine. The Miami Sound Machine was not credited because this was like a solo album, but they are the backup band, and they rule. And this album rules. This is Cuts Both Ways from 1989. Yeah. So back to our little repair here. First things first, some safety precautions. Wear gloves. I should actually have some thicker gloves than this. You're working with AC mains, so this is incredibly dangerous. I would highly recommend, I don't know. I'm not responsible if you die, okay? So, like, be smart and, I don't know, be careful. Ideally, I would have this with a better insulated workbench. I'd have better gloves. But this is what I have to work with, and also I'm stupid sometimes. So, yeah, take that with a grain of salt. I'm not responsible if you hurt yourself. You are watching this video at your own risk, and you are taking things apart at your own risk. Now, this is a Fellows lamination machine. The Fellows is just the brand, obviously. I bought one of these broken because I was curious about taking one of these apart and learning about it. And I didn't actually save that much money. I think I saved $10 buying a broken one instead of a working one. But I also saved something from going into landfill, which is cool. I do care about the environment. And yeah, it's a pretty curious little beast. So first things first, of course, I have it unplugged right now. This will actually switch off the AC mains as well, which is useful for testing, depending on how careless you want to be, I guess. The way this was installed also is worth noting. It's kind of cool. You see these little tabs sticking out on the cutout around the PCB edge. Well, those actually slot into those slots there. It goes vertically like that. And then screws with two screws with, like kind of the built-in washers around the edge. Hold it in. I thought that was a kind of a cool way to mount a PCB. So kudos to Fellows for making kind of a cool PCB mount. This beast is pretty simple, of course. It's just a very large heating element with two rollers that turn when you feed in the laminate. And there's a motor, of course, doing the turning. This is like the release switch, which disengages the gears. As you can see, there's 3 gears there. There's the primary motor gear. Let me get some better light here. Yeah, this video quality is not what I would like it to be. But yeah, you see there's 3 gears, and then this physically moves the motor out of the gear path, which is kind of interesting. And also kind of interesting that the motor gear is a little bit like off center for the other 2 gears. I thought that was kind of interesting. But that's just what it is. The motherboard. So I was interested in learning about how this thing actually functions, and I had to do a little bit of education for myself, which was cool. Because it uses triacs, or a triac, and I don't know much about triacs. They're kind of an older technology, and they're only used in, mainly used in AC current control. This is the triac right here. So they're used, I guess they're used in like cheap light dimmers and that sort of thing. And I would like to build some light dimmers at some point, so I was kind of interested in learning about it. This is the plug orientation, as you can see, and a little bit of a rundown about what's going on here. So you got these two brown wires are basically the main switch here for turning AC on and off. That's just a hard switch for the AC. Kind of useful, kind of strange. I would think they would just have like a, toggle switch on the back or something. But I guess this is for ease of access, and it makes sure that it's completely off. So whatever. It's also kind of surprising they didn't use the microcontroller to do any sort of switching, and they actually resort, even though they have one, they just use a big fat button. You have a fuse there, of course. Nothing was wrong with the fuse. I will say what was wrong with this, by the way, is it wasn't getting hot. So when I ordered this, the person said it wasn't getting hot. and everything else seemed to work. This is where your mains comes in, obviously, big thick wires there. So then you have your fuse, then you have your switch, your on and off switch. All right. So once it gets switched on, you have a large resistor there. I'm actually not sure exactly what that resistor, I guess it's just limiting the current. But you have your bridge rectifier, which is really just diodes, which is what a bridge rectifier is anyway. And then you have these two capacitors here, and what it's actually doing is it's creating 12 volts from this capacitor bridge rectifier. This is a large AC capacitor, I believe, as well. It's just making 12 volts from that. And then this little, this is a tiny little 5-volt step-down regulator. It might even be a 7805. I haven't really looked, but anyway, it makes 5 volts. I don't think that 12 volts is actually used for anything. I believe it's just easier to step down to 12 than it is to 5 from mains. And it's also, what it is it's not regulated very well as 12. So this helps regulate the current. And so that 5 volts is used to feed this microcontroller, to power this microcontroller right here. Obviously, it's some little custom PIC or whatever. It's kind of cool. You can't really see very well, but see, maybe you can. It says Saturn, and then whatever the other brand is. They have 4 different types of laminators, and this notch here tells you which kind it's programmed to fit in, which is kind of cool. Also, you have a notch here for the different voltages, if it's European or just, even Brazil has 220 volts. It doesn't necessarily mean European, but it just tells you the voltage range, the phase. Oh, and this just broke off while I was making this video. Psh, whatever, it's not too hard to fix. This, by the way, I'll get into that in a sec. So there's a little buzzer here, microcontroller controls. I'm actually kind of interested in what these components do. I think one of them, this blue one, actually I think I know what they do. This is for timing. This is for creating a clock frequency. That blue guy, yeah, Y1, that's a crystal. So that creates the clock that's necessary for the microcontroller to operate. I'm not sure there's so many capacitors, but I guess they're doing the capacitance matching for the crystal. So we got that down. We understand our 5-volt stage pretty well now. This plug right here, by the way, these are outputs. You got these resistors here. These are all outputs, and those are just to control the LEDs. Green LED, red LED, 4 wires, or it's 5 wires, but there's grounds on each side. I don't think there's a signal wire in here. I'm pretty sure this is just LED outputs. Which are signals, to be fair, but there's not an I/O going on. There's not an input. So that harness goes straight to here. It basically is the microcontroller telling you it's still heating up, and the green one saying it's ready. Put your laminate in. That's pretty simple, right? And then what else is this microcontroller doing? Well, it's also talking to a thermistor, and that's what this plug is, which just came off, which is not too hard to fix. There's a very interesting looking thermistor in here. This is a pretty specialized thermistor because, for one, it's got a spring, and I think that's because it's needing the tension to push itself against the rollers, because it's trying to know the temperature of the rollers that are coming into contact with your laminate sheet. And it's also going to have some metal shielding, I believe it's connected to as well. And so that thermistor is what tells the microcontroller, okay, it's hot enough, it's at this temperature. And the way a thermistor works, and it's probably a negative temperature coefficient, or NTC thermistor, the way a thermistor works is it's either a positive or a negative temperature coefficient, meaning the resistance will change from 0 to usually 10K, depends on the thermistor, at a certain curve. There's a curvature to it, based on the temperature rising, or it will change from 10K to 0 based on the temperature rising. And usually they're used for temperature rising. I guess if it's negative temperature coefficient, it could be for getting cold as well. But yeah, basically it's a type of resistor. An NTC is just a type of resistive element that changes resistance with temperature. It's pretty simple. And it's a cool way to indicate to a microcontroller when something's changing temperature, because it's doing it just with resistance. It's not high voltage, or it doesn't need, you don't need to have like some sort of special temperature sensor, monitoring system. It's like a quick and dirty way to tell temperature, basically, without a ton of accuracy, but it does it well enough. And so when that happens, the microcontroller knows, okay, this is roughly at, 250 degrees or whatever. I think it's 270 degrees to heat up, to be the proper heat for laminate from what I found online. Then it will say, okay, I can switch off the triac. Now it controls this triac, and it also seems to control the motor. You know what? I take that back. It does not control the motor. So what you can see here is the motor actually, I believe, is just always on. So as soon as you switch it on, that motor's just going. That's what I've found in my testing so far. And the red wires, surprisingly enough, the really thermally protected wires, are not for the heating element. Those are actually for the motor. My guess is they made it that way because it goes behind the heating element. They didn't want it to melt, which I guess makes sense, but it's still weird to me that the heating element are these kind of thin black and white wires. They look like maybe 22, 24 gauge. And so, yeah, that motor is pretty much always connected to the mains. That motor plugs in through these two contacts to the right of my thumb there. Let me get out my tweezers, actually. Keeping in mind this is not plugged in right now, and I'm being careful with gloves, and there's also not any large output capacitors, I believe. So, yeah, so this is your motor right here. And you can see there's a path to ground along this edge. And then I believe this is the input path. And gosh, I haven't traced everything out, but or I didn't like draw it out on paper or whatever. If I really wanted to, I would do that. Maybe that's what that large resistor is for. That might be for the motor. Anyway, it doesn't really matter too much. What is interesting though is that, so basically what is important to know though is that there are two resistors right here. One is a 1 mega ohm and one is 330 ohms. Oh, sorry, I'm trying to rearrange this. So you have a 1 mega ohm and a 330 ohm resistor. And they read R6 and R5. Now, those two resistors go directly to the microcontroller, and you can see this. Here's one leg of the resistor going to the microcontroller. Here's the other one, which wraps around, goes to the microcontroller. Now, those are I/O pins, GPIO or whatever, and those do control. So one of them goes to the gate of your triac. This is your triac right here, by the way, these 3 pins. This triac is a BT13600E, made by NXP. It's made by NXP. They changed, they had a merger, so this couldn't be that old, because NXP didn't exist, I think, 5 years ago or 10 years ago. Maybe even more recent than that. So that controls your triac, and that does a current control. And you can see here that the output to the triac goes to this plug. So yeah, my guess is this is, and then this is connected to the microcontroller as well. So the microcontroller, interesting, I think it's doing a feedback. It's measuring the output here as well as controlling the triac from here. And so that's just doing, it's probably doing a PWM pulse. I haven't put my scope on it yet, but that's most likely what it's doing. So what was interesting is I actually could unplug the motor and the heating element. They're the same plug. They're both 2-pin Molex plugs with clips on it. Don't know the exact part number, but you see those plugs everywhere. Those two right there. And you can actually swap them. They're actually interchangeable because they're both AC. They're both running off the mains at 120. And if you do that, you'll actually get the heating element getting real hot right away. It starts really cooking because it's just getting straight 120. Whereas the motor, it won't work because whatever's going on, it's not giving that 120 to the other output. And that's how I found out that the heating element's fine. There's nothing wrong with the heating element. Something wrong with the output to that plug. Okay, so we know there's something wrong with the output of the plug. What's the next step in troubleshooting this? Well, I basically rounded it down to 4 possible problems, 4 most likely problems. 1, cheap solder, bad connection somewhere, cracked solder joint. Very common with high voltage applications, so real easy to just quickly reflow everything. So that's what I did. Reflowed everything with fresh solder. That takes all of 2 minutes. Didn't fix it. Okay. Not, you know, that's never like a super, not a super common thing. I do see it, but it's an easy thing to just start out with. Okay, so that didn't fix it. What's the next thing it could be? Well, it could be a bad triac. If the triac's dead, then you know, you're definitely not going to get any output power. So when I measured this, there are ways you can test the triac, but I will say that if a triac goes bad, it's probably going to be either a dead short, and very likely it's going to blow out the microcontroller too. Dead triac, you'll usually see like a burn or something real nasty because it's doing high voltage stuff. And I mean, that's my guess. Like I said, I haven't worked with triacs a lot, but I have worked with high voltage stuff a lot. And to see this resistor looking in perfect condition, as everything else on the board does, it would seem unlikely that a triac would have blown. I don't get any dead shorts anywhere. Just doesn't seem likely. So what I did was I turned it on and just measured what was this gate doing. What was this gate doing when it was on? And what the gate was doing is it was pulsing. It was actually very quickly pulsing to an on state, but to the point where this would only output, you know, 1 volt AC. I mean, basically not on. And so it seemed unlikely to me that the triac would be bad if the gate is actually pulsing something and there is output voltage being created. Now, that doesn't mean it's not bad. It just means it's less likely to see a failure state in that way. Also, I started to believe the microcontroller was okay because, like I said, it was pulsing. It was trying to do something. And again, that would be if the triac went bad or the, you know, power input was fried on the MCU. That seems unlikely too. And of course, I measured the 5 volts coming off this regulator, and that was fine too, as was the 12. So your voltages are good. Triac appears to be doing something, and your microcontroller is telling it to do something, but it's just telling it to do it in a weird way. Okay, well then, what does that round it down? That rounds it down to the 4th thing to check. What is that? That is your thermistor. And a lot of people might even start with checking this, but I wanted to check all the other stuff first. Because I didn't know what resistance this thermistor was. I didn't know if it's a negative or positive temperature coefficient. It doesn't look like it's a part I can replace, you know, from the manufacturer. And so on a whim, I was like, okay, well, first off, when this was plugged in, it was always measuring 0. That seemed kind of like a strange failure state because if it's 0, usually when a resistor breaks, it's an open circuit. It's not a 0. And that actually seemed to me like the resistor was probably working. Now, there's a way you can test this, of course. You can plug in the heater directly here, get it really, really hot, and then see if that thermistor is changing resistance the way it should. But I didn't actually do that. I just had a thermistor in my parts bin. I have a bag of them. This is just a typical 10K. You can also just take a 10K resistor and put this across. Now, some thermistors are 100K. Some of them are different. 10K is just kind of the most common. So just kind of went with that. And what do you know? Soon as I wired this up as a 10K, started pulsing the triac more frequently, and it started to help the temperature started climbing in the way that it should, not just giving it 120 direct. So the heating element just, you know, freaking burning, which is a hack. Like that could have worked with a big switch, would have been a little dangerous. Not really my favorite way to go about things. But for my personal use, if I just wanted to do a hack and make a toggle switch for the heating element, you know, maybe find a temperature readout meter for cheap or something, you could do that. Kind of a fun hack. But I wanted to get this working, you know, the way it's intended to, if possible. And so, yeah, now I know it's actually the thermistor that went bad. And it's not entirely shocking. So what I'll do is I'll take this out. I'll see if there's a short on the wiring somewhere. Seems unlikely, but what I can probably hopefully do is find out the part number, because I do want to know how it ramps up or ramps down, because the microcontroller is going to be programmed according to the specs of whatever thermistor is being used. So an exact replacement would be ideal. And then I'll have a working fellows. Laminator. I'll just put it all back together. Have a nice working laminator. And I will have saved myself $10 American. I don't know if there's anything more exciting than that. More importantly, though, I will have the power of knowledge. And as they say, knowing is half the battle. This is Sega Sonic Fan. I hope you learned something useful here. Check out my other videos if you want to learn more stuff. And I don't care if you like or subscribe this because I'm not in it for the money. Sega Sonic Fan, signing out. Yay!